Hello, my name is Ohad, and I will present the paper Late to the Party, On-Demand, Unlabeled, Personalized Federated Learning. In federated learning, multiple clients collaborate to learn a shared model through a central server while keeping the data decentralized. We now present a simple way to demonstrate how it can be done. First, the server sends an initial global model to all clients. Then, each client uses its local data to fine-tune the model. All clients send their model to the server. The server aggregates the model to produce a better global model. We then repeat those steps iteratively. Data distribution may vary across clients, and one global model may be suboptimal solution. In personalized federated learning, we learn a personalized model per client. For example, each client can fine-tune the global model locally. Sometimes, after a system was trained on a set of clients, a new client that has no labeled data may wish to join the party. We call this setup On-Demand Unlabeled PFL. We wish to apply a system that was trained on a set of clients to a novel unlabeled client. In both federated learning and personalized federated learning, all clients participate in the training process and the labeled data are used for the training. How those methods can serve a new client? In federated learning, a new client may use the global model. This may be suboptimal solution if there is a gap between the distribution of the clients. For personalized federated learning, it is less clear what is the way to produce a model for the new client. We aim to train on the labeled clients an architecture that can be applied later on new clients with no labeled data. First, the server sends all clients a client encoder. Each client applies the encoder to its private dataset and gets a descriptor for its local dataset. In the server, each descriptor is fed to a hypernetwork that produces weights to a client local model. The weights are sent to the client to create a local model. At training time, each client uses its own labeled data to fine-tune that model and propagate the gradients to the server to update both the hypernetwork and the client encoder. At inference time, we can skip that step. To summarize, this is the whole process. In the paper, we investigate the properties the client encoder should have to be effective. We evaluate our approach on 5 datasets, and we find our approach consistently outperform other baselines. We also evaluated the robustness of our approach to corruption by applied corruption to the data of the novel client, while the data of training clients was kept uncorrupted. We also analyzed the privacy of the novel client and characterize how it can protect its data by applying differential privacy to the client encoder. To conclude, we describe a new federated learning setup, On-Demand, Unlabeled PFL. Applying federated learning and PFL methods to that setup leads to a suboptimal result. We suggest a method based on hypernetworks that can handle novel unlabeled clients by design and show its effectiveness on both label shift and covariate shift data. We further show that our approach allows each client to apply differential privacy on its data. Thank you.